Now, very happy and proud to introduce Dr. Jason Held, who's also a co-founder of Delta V. For those of you who weren't here earlier, our accelerator program that we want to run here in Australia, and he's also the CEO and co-founder of Saber Astronautics. He was a former major in the US Army Space Command. I'm going to steal your joke, so you stick to time. Came to Australia, got a PhD and a wife. So we got to keep hold of him.
I got the bonus plan, that's the joke he's trying to tell me.
Over to you to talk about space ops and how that's going to change the game for us.
Okay, right. Thanks for that great introduction, Tim. This is my second time coming to this workshop. I realized this morning that I just put on exactly the same shirt as I did last year.
Hopefully
do not be alarmed. I do watch it.
Did you watch it?
I do watch it. All right, one thing that I always note when I come to these talks is space mining is one of those very forward future type of things, and that's why I love it. And there are companies that are trying to do it and making a lot of noise right now that are saying, okay, we're going to do it in the next few years, and they're engineering things, and I love that too, because that means that myself as a space engineer, as an entrepreneur, I have somebody that I could go to and sell my product to that could actually use it and actually needs it. But very often I talk to people that are thinking this far forward. They're not thinking of the kind of how-to. They're thinking, okay, send a big spacecraft and pick up an asteroid. No, nobody's really saying that. What they're actually saying, because they know they got to get market entry. So let's send a whole bunch of smaller ones out there, pick smaller amounts of material, and make it more manageable, which is a very sensible thing. But it's a very, very hard thing to control. A lot of problems with that, and that's what we're going to just kind of touch on. First, a bit about us. We are a small company based out here in Chippendale, Boulder, Colorado. Just about 5 or 6 people in each lab, but we packed a lot of technical punch. We got folks who worked on Hubble and the ISS. There it is, in case you don't know what they are. All you should know in this room. We got 2 PhD graduates from the world-class robotics lab out at the University of Sydney, and decorated officers from Army and Air Force Space Command. So if you think about that skill set, it's very much within space flight, software operations, and diagnostics. All right, so back to mining. This is the problem you guys are going to have once you're at that point where you're actually sending stuff out there. It's environmental conditions, it's radiation conditions, and it's also your own headspace and timing. You know, it's your own errors that you're going to put into your own products. The conditions, this just comes as a spot check for me out of the asteroid belt. You find minus 108 to 73 degrees Celsius. Radiation, and feel free to push back on me. Some of this, I know some of you geologists looked into this more deeply than I have for this talk, but mostly it's galactic cosmic radiation, and it's also design errors. And as the example, this is the spacecraft that recently did flyby of Pluto. Right? I love Pluto. To me, it's still a planet. You know, no matter what they say, I'm a hard line. Right? All right. All right, enough of that. Not the fight right here, right? I love you guys though. All right, but some of the things happened in that mission that you guys should probably keep aware of as you're thinking about your own asteroid mining plans, right? The spacecraft died. It completely reset. They went into safe mode a few times. Happened more than once. Scared the living bejesus out of everybody who was waiting over a decade to see their data. But like the good engineers they managed to get it up and running. All right, so what are the actual effects? Well, there's 3 different types of faults you can get on any spacecraft. Single event upsets, that's when radiation, don't try this at home, kids. Take a magnet and run it across your computer. All that radiation is going to do all this funny thing to your chips, turn zeros into ones, and cats and dogs living together and all that. Basically what happens, the way we handle it in modern spacecraft, is you turn the whole computer off, you turn it back on again, and you keep running, which means, well, this thing is so far away, you know, it's going to take, if you're around the asteroid, it's going to take probably up to, I don't know, 60 minutes, about an hour to find out whether the problem existed in the first place, and then you're going to find out whether your control actions actually saved it. And maybe it stays dead, you have no idea. Right? Well, luckily, a lot of that's done automatically. There's also false positives, where a 0 turns into a 1, and what you see on the screen is you might see faded data, discoloration, So, you know, from your perspective, you might think it's copper, but it's really nickel. I'm kind of making this up, but the cause is really the same. The effects we could all kind of imagine in our heads. And at the end of the day, there are a lot of diagnostics challenges. So whether you're on the Earth or whether you're the autonomous system in space, you know, what's wrong with the spacecraft? I have no idea what the root cause is, because everything's turning red, and which one of those little red things is the actual defect, and what do you do to fix it when that spacecraft is so far away? Let's take the simplest example we have in industry right now, which is the CubeSat 10 centimeter by 10 centimeter cube. We've all heard of them. They're doing wonderful things, leaving university, now entering the market, scaring the pants off of the Boeings, Lockheeds, and Northrops. They don't know what this is going to do to their cash flows. But everyone's excited about them. But diagnostically, even this simple satellite, the robust ones, I'm finding have about 100 health sensors on board. All right, so apologies to the geologists in here. I might show a little bit of math. Avert your eyes. If you're to say what the root cause of the damage is, it's 2 to the n minus 1 over 2, so super exponential to the number of sensors. So 2 to the 49, let's just say it's infinite and move on, okay? Now, you know, these swarm constellations we all talk about that we're going to use for asteroid mining, or maybe a large logistics infrastructure, multiply that number by the number of satellites, and that's the complexity you have trying to find out where the problem is in this mass problem. All right, now, some of you who are traditional mining folk, and I know there's a few of you I've met already, replace the spacecraft, put in a truck, put in a person, you get the idea. Put in a pipe, it's the same problem, all right? Also, the way we do operations today hasn't really changed paradigm since we first started in the 1950s. It's a bunch of people sitting in screens, looking at a whole bunch of words on a screen, waiting for one of those little words to turn red. Red means there's a defect. Defect is bad. You drop your coffee, run to your seats, and you say, oh shit. Because a defect on that satellite, if you don't fix it, is hundreds of millions of billions of dollars worth of wasted effort. Or in this case, this is a docking maneuver, it's life of crew. But we're not going to talk about that. We're just talking about money. Right? So at Saber Astronautics, what we've done is we've taken this and turned it into a video game. All right, so think visualization on the front end, data analytics on the back end. We call it the Predictive Groundstation project, affectionately PIGI. And we run it at an operations center we call the RSOC, the Responsive Space Operations Center, and here's what it looks like. All right, 150,000 stars in the Hipparchus catalog. Forget about 2D words on a screen. Now what you're looking at is data-driven, live data feed from the Space Weather Protection Service out of Boulder, Colorado. That's the same data feed the governments get. And you're looking for solar flares, so you're going to fly around and look where the solar flares hit. The star chart's important because you want to be able to simulate attitude control, so you're trying to do planning of large satellite maneuvers, you can do that. You get day-night cycles, so you can calculate heat and cold. We've got we download the NOAA SatCat straight to the tool, so adding a satellite to the simulation is very, very easy to do. We just have the ISS at a default. You can set your own, doesn't matter. And then just to show you that you can propagate forward, our orbital propagator is within floating point error of NORAD, so it's very accurate. And you see these little bars up here? That's when your spacecraft is flying over a ground station. That's when you could actually talk to it to find out if it's dead or if it's alive or if it's actually picked up the material you're looking to pick up. Great. Okay, what's next? We're just going to let it sit here and look pretty for a minute. There you go. There's your 130 satellite constellation. Just to show you that we could do it. This is really just pretty pictures at this point, but propagating forward. So you could propagate large numbers of spacecraft without any real problem. And just for fun, I think at some point we speed it up. Because what you're going to want to do is maneuver planning for spacecraft. It is a high trained task, and you want to reduce that training effort on yourself. So you're going to be able to put the commands right into that timeline bar at the very top. Okay? So all right, now we're showing that you can go to all the planets. See, we've got all that in there. We're about to put asteroids in there. Tried to get it in time for you guys. We're only a few weeks off of that, actually, but it's not that hard to do. And with a lot of data, of course, you have to have watch variables and favorites and things like that. But this is important. You got a defect on the satellite. You got the telemetry embedded right in the system. It's point and click. right? So you only need one person to do this. You could open it up, you could look inside the guts of the satellite. So you think in terms of thousands of data points, hundreds of thousands of data points. Now it only takes one person using it like a video game, practicing those Xbox skills like we've been doing since we've been 13 years old. And then you could run this. And we've tested this with high school students, and oddly enough, the best demographic to use this tool ends up being middle-aged women. All right, the middle-aged women using this tool are outperforming the teenage video game experts. Not sure why, but I think that's awesome. I think it's absolutely awesome. All right, how much time do I got? That doesn't matter. All right, so front-end graphics, data on the front end from heterogeneous sources. On the back end, you have diagnostics. So old spacecraft diagnostics screen with telemetry on it, so you're looking at temperatures and voltages on the spacecraft. We pipe it into performance metrics. Then we're going to find a relationship between those performance metrics to pipe onto the screen. Cause and effect. The circle represents variables, the arrows represent the effectors, what's being affected. So, and we have a formal process for choosing variables. But if you think in terms of cause and effect, you don't just want to say that solar weather has an effect on, say, your electric power subsystem. We know conceptually that's true. You want to actually quantify that with a number, right? So we use a variety of machine learning techniques. In the interest of time, I'm going to, and the sanity of the geologists, I'm going to breeze through this. All right, so if you want to know about some of the maths, come after me afterwards. So you're talking Bayesian networks, Gaussian mixture models, and what you're doing is you're finding the highest point of a likelihood curve of this number regressor given observations in your data set, where the observation are the metrics of performance, okay? And we discretize the data sets into different states. So it's kind of like, if you're measuring a human being walking down the road, sensors on the elbows and the wrists, and you do a Bayesian network of the person walking, that network's going to be accurate over time. The moment you start hopping, and I only do this because I like Dancing with the Stars, the moment you start hopping, those regressors are inaccurate. You have to retrain them. So what we do is we fit this with the mixture model, discretize it into groups, and then we switch models between the groups, okay? So let me move on to some of the results that we did with a NASA Goddard study where we tracked 23 performance metrics. And we took, they gave us their entire data set. We're really grateful for that. We took 2 weeks of data from the 2003 space weather event, largest space weather event in recorded history. And we tested the accuracy of our diagnostic model on 2009 nominal and 2011 hazardous data. So what we're trying to get is time invariance, as in the model is good over time, and general solutions. So if you've got a high space weather event or a low, it doesn't matter. You don't have to retrain it. Remember those three events that could happen. On the left-hand side, you've got truth data. On the right-hand side, you've got output from the model. This is nominal condition. All right, so the model was trained off a very variable event. All right, this is nominal condition where everything's on the straight and narrow, everything's quite happy. Then you got these spikes. You know what those are? That's what a single event upset looks like. Everything shuts down and comes back on again. All right. We're actually able to model that up to 85% of the time. This is, if you're in the machine learning community, this is called a black swan. All right, it's supposed to be an unmodelable event, and to our knowledge, we're the only ones doing it. Hazardous tests. Again, you've got more variable systems, so a large space weather event happens, the temperatures go down and up, and the spacecraft's affected, and we can track that with really high accuracy. But you see these? This is what happens when the radiation hits a sensor. So this is saying the temperature of the sensor is lower and higher and lower and higher, but the reality is the sensor is being degraded. It's a false positive, and we're able to get rid of those. And the piece de resistance for us, this is where we started, popping champagne corks, is we're actually able to go back from the actual spacecraft performance into the radiation event that caused the damage in the first place. And we're dead on accurate, so we know it works. The latest stuff we've been doing is we've been doing space weather protection. We're up to about 3 hours look ahead using neural networks, shows you the truth and the outcome from our estimate. That's because the radiation data that you get by the time it gets to you as the operator is actually about 3 years old. Sorry, 3 hours old, not 3 years. And the idea also is if you could diagnose the performance of a spacecraft at the ground station, can you also put it on board the avionics? So under a NASA Phase 1 SBIR, we developed up to Tier 04 a bench prototype of some avionics which can autonomously reconfigure itself based on radiation, thermal, your neighbor's thermal. So it's not greedy, it actually helps out the spacecraft as a whole. So we're actually on the hunt. We just got word that we got a grant for a space flight on the ISS for 6 months. We now got to raise the money to finish this product off before we can fly it, but it's real good news for us. Think of this as the precursor to a transformer. That's kind of how we do it. Transformers, more than meets the eye. Okay. All right, so you guys get it, real high accuracy. We are commercial live. And we picked up some customers that are really good customers I can't talk about because there's a video camera on here. But that's all I'm going to say in the interest of time. What are your questions?
Questions for Jason? Okay. Yes.
Has it,
Tom.
like your AI or your machine learning tech and the algorithm, has there been interest outside of the space community in that alone?
Great question. Yeah, actually, that's how we've survived.
Sorry?
That's how we've survived.
Right, okay.
That's how we've survived because we were in R&D mode for 4 years. We've done paid contracts for search engine optimization, well, not search engine optimization, paid contract for water utilities. We've done paid contract for human robotic interactions. That was with the Mars Society out in Arkarula. Interesting result, we're able to track the heart rate of the astronaut based on the performance of the rover. Really, really fascinating stuff that we're digging into a bit more.
And you got a live pitch with the telco industry, which is woken up to how amazing this is going to be for their world. So.
Oh, yeah, sure. We've done quite a few. We've done pretty broad, all right? And we don't search it out, but sometimes it happens.
Terrific. Yes. Go ahead.
I had a question. In terms, like, you said you were importing asteroids shortly.
Yeah.
Are you creating like a toolkit for people who, like, if they discover a new asteroid, getting better information about asteroids and comets and things like that, for them to be able to import this into your system?
Yeah, we're pretty stoked about that, actually.
It's Kerbal Space Program is really popular. I would love the idea that you can import models, import planets, and like that idea that.
Yeah, you notice the star chart in the beginning? We're actually looking at planetary bodies there. That was what we got started down that path. We have a data API that we have released in test mode, right? So people who want to try that, let me know. So if you put in your own, you could put in your own asteroid soon. Right now, you could put it on your own spacecraft and use the data API to manipulate it. Putting in parts of the API to manipulate the graphics as well. We're not too far off of that.
Cool.
Okay.
Thank you very much, Jason.
Thanks, geologists.